So there's 60 degrees C water coming out. There's a few losses as this is transferred to the houses, but you actually get quite a lot of it used in the houses. Now we spoke about ground source heat pumps, and what this is where you can drill and put, typically it's a plastic pipe that gets put down quite deep into the ground. Typically depths are 100 meters or a few hundred meters. You pass water through this from a ground source heat pump, and as the water comes back up, the hotter temperatures from lower down, you can extract the heat in that process and use that in your property to heat. Or indeed, what you can do is pump heat down this so the ground absorbs it and use it to cool properties as well. So in fact, you can design systems that allow both heating in winter and cooling in summer, and therefore it's very practical. Now, it's a very high initial capital cost because mainly you have to drill holes and put holes down, but then it's only the electricity for the heat pump you actually consume when you're running these systems. Now, the energy that you have from ground source heat pump, you can see here we've got the thermal conductivity of different materials. So hard rock is about 3 watts per meter Kelvin. You then have saturated unconsolidated. This is basically where you have earth that has water in it, or if it's dry, so sand is an example here. You can see there's different thermal conductivities. The ability to extract energy from this per meter, you get about 80 watts per meter of pipe that you have if you have hard rock. Now, the problem with hard rock is you've got to drill to get your pipe through there. So this is much more difficult to extract heat out of and much more expensive to do, but there's more energy available in those types of rock. If you've got earth that it's much easier to drill a hole and put a hole down, then you can see it's less, but it'll be cheaper to actually put this in, but you need longer pipes to get the same amount of energy out. So here the energy per meter of a typical borehole, so this is kilowatt hours per meter length per unit area. You get about 135 kilowatt hours per meter of the borehole. When we go to things like dry sand, that could be 65 kilowatt hours per meter per unit area. So for the amount of energy you need for a property or for an industrial building, you need to work out the length and bore of the pipe. So you can see this is looking at a bore of 1 meter wide. In reality, what real systems actually have is a much smaller bore. And so this number is per meter squared in terms of width. So you can understand this is a lot less when you look at the typical pipes that are used. So to finish off, we've spoken about in the last lecture the Carnot efficiency. So here's the delta T's that we've got. Here's the efficiencies. And as I showed, as you get up to 700 degrees C gives you 70% Carnot efficiency. The coal-fired power stations, the most efficient ones that are available, are now up to about 42% efficient. And that's really because they run at just below 600 degrees C delta T's. If we add carbon capture onto those, we actually end up with 20% reduction, and you can see that we're only just above 30% efficient. Nuclear power stations run at lower delta T's. So here the is a little bit lower. In fact, if we could increase the delta T here, and some of the newer designs are doing that, you can increase that efficiency, and you end up having longer periods of time before you have to refuel the reactors, and you get less waste coming out of the system. So this gives you at least examples comparing efficiencies of some of the systems we've looked at today. And we'll add to this in the future, which is what some of these other lines on the graph are actually trying to do. So that's what we have in the power stations. One of the things, we're talking about, let's say, a nuclear power station, and you have 35% efficiency that generates electricity. That means that from the fuel we started with, we're throwing away 65% of the energy, and that energy is typically going into heat. So in the Rankine cycle, we speak about the condensers. Most of the loss actually comes from those condenser systems. So you typically use these towers, and these are cooling towers. Now, what you see going out the top is actually just water vapor, and you have the hot water in the Rankine cycle coming around. That typically goes through a number of sprinklers, it condenses in that process because you also have joule Kelvin expansion. It then gets collected, but also some of this evaporates, and that's why you see the steam coming out the towers. So you also typically have to have makeup, and this is why many power stations are close to rivers or close to seas, so they can take water in and make up the power stations. So what you're actually doing is a lot of the 65% loss is going out through the steam that comes in these cooling towers and from just trying to cool or condense the water in the Rankine cycle. So why not try and take some of this heat loss, and rather than throw it away to the atmosphere, why not try and use it for something useful? And this is the whole basis of what combined heat and power systems do. So this is what's known as the Pimlico accumulator. This is taken hot water from one of the power stations around London, transported it and stored it, and then this is used to actually, in a district heating scheme, to heat the flats that you can see in the background. So now taking the 100% fuel from that power station, rather than 65% of the heat being thrown away, it ends up overall about 20% of the heat is thrown away from the original starting of the fuel. So 30% in electricity comes down a little bit. District heat gets about 50%, and the losses are about 20. So there's less overall losses, and rather than putting all the condensation into the atmosphere, we're using at least some of that heat. It's very difficult because of the laws of thermodynamics to get zero loss, but we can at least reduce the losses quite substantially. And that's really the great advantage of doing combined heat and power. So for today, that's basically us finished. So we've spoken about carbon dioxide, sulfur dioxide and acid rain, radiation and carbon capture, and coal-fired power stations. We've spoken about electricity generation from biomass, crops and waste. And we've also spoken about electricity generation from nuclear power. So at the moment, coal and nuclear power are used as the base loads in most countries. And this is because they are such large generation schemes. They really set the phase of the national grids, and they're the ones that everything else has to phase lock to. Now you can see that what's seldom discussed is when you move to renewables and much smaller renewables going onto the national grid is how that's going to work, because you need these base loads really for a national grid to function correctly. Geothermal and ground source heat pumps we've spoken about for low CO2 sources, and combined heat and power for improved efficiency. So in the next lecture, we're going to go through solar, both solar thermal and solar photovoltaics. For the final slide, in fact, this has just been updated literally 2 weeks ago, but the Scottish energy policy, the Scottish government came out with a new energy policy in 2017. And it came out just before, in fact, I gave the lecture 3 years ago. Now, there was all the media doing all these things and saying how wonderful it was that Scotland had managed to reduce its greenhouse gas emissions by 45.8% from 1990 up to 2014. And it was saying this was all because of the Scottish government's policy in renewables. Well, actually, the biggest reductions was because there was an enormous reduction in heavy industry with shipbuilding, steel, and aluminium production in Scotland. So most of this 45% doesn't come from changing from coal and moving to renewables. most of this greenhouse gas emission reduction actually comes from the reduction in GDP and the loss of industry, and also less heating of properties from warmer windows. In this policy, there was nothing about transport or heating. And in fact, a couple of weeks ago, that's the first policy that has a little bit on moving towards electric vehicles, and some discussion about heating for the first time. So there was all this PR that went out. You can see it was 24th of January 2017, virtually 4 years ago. And the bit that nobody in the media reported was that the Scottish government is very anti-nuclear. So for the base load, their proposal at the time was to replace the 2 nuclear power stations for the base load in Scotland and replace them with coal-fired power stations, which would substantially increase the CO2 emissions. Now, the report that's come out a number of weeks ago has now changed this from coal to thermal. It's also spoken about coal with carbon capture as the 2017, but at the moment, as I've said today, carbon capture is nowhere near ready for being used on these systems. The 2 nuclear power stations in Scotland have to be decommissioned by 2023. So within 2 years, Scotland is going to have to build new coal-fired power stations for its baseload if you go with the Scottish Government policy. And carbon capture won't be ready for that to happen. So you can see here that everything you hear from the Scottish Government is saying about renewables, renewables, renewables. But actually the baseload is absolutely key in terms of the carbon emissions and what's going to dominate here. And very few people ask questions about that. So if you get a Scottish politician talking about energy, you should ask them about the baseload, because that really is a key question for Scotland's future energy and carbon emissions. So that's me for today. So a lot of what you need to think about in terms of the carbon emissions and what we've been talking about today. You can see here, nuclear is much lower CO2, and compared to a lot of the renewables, it's also very low with renewables. And there's the fossil fuels. So the Scottish Government wants to move from numbers around here back to this number for the base load in Scottish energy. So that's me for today. Let me just stop the recording.